Hi guys, welcome back to the channel. We'll continue with the 450 questions DSA series. In this video, we will finally finish binary search trees and we will move on to the next topics, which is greedy and then backtracking. So greedy and backtracking together, they have actually very nice problems. In greedy, there are nice podge problems. Backtracking itself is a big topic actually, and nice set of questions are over here. So we will quickly finish with binary search trees in this video. If you have still not yet seen any video, please do check out the playlist. I have finished so many topics. Around 200 plus questions are done. Please share this with all your friends in all your WhatsApp groups. Ask them to subscribe and ask them to support me and like the video if you really like my work. So let us start with today's problem. Today's first problem is given a binary search tree that contains positive integer values greater than 0. Okay. We have to check whether there is a dead end in the BST. What do you mean by dead end? So dead end over here means if we are not able to insert any element after that node. So I'll explain this to you with the test case examples itself. So we are being given a function and we have to return whether we can, find out if there is a dead end or not. So what is a dead end? So let us consider this example. I'll show you what is a dead end. So say for example, the BST is this. Okay. Yeah. So this is our BST. Now, according to the problem, what they're trying to say is this node with value 1, this is a dead end. So first of all, we have to understand that only a leaf node can be a dead end. Can be. It is not necessary it has to be a dead end. Only a leaf node can be a dead end. So this is something that everyone should understand before proceeding. Why only leaf node? If we take a basic example, suppose this node cannot be a dead end. This node is never going to be a dead end. Dead end means what? We can't insert any other node. That doesn't mean that, this is a dead end. Just because we can't insert, see, we can remove this 7 and put 6 over here, something like that. So this is never a dead end. So dead end means we are only concerned with leaf nodes. So I hope this much is clear, okay? And now let us see why this node with value 1, why is it a dead end? This is a dead end because if I consider 1, to the left and right, if I have to insert some values, what values can I insert on the left and right of 1? To the left of 1, I can insert a value, any value which is less than 1. And to the right, I have to insert a value which is greater than 1. But let me remind you, we have to only go with positive integers and 0 is not a positive integer. So to the left of 1, I can start only with 0. I can do 0, -2, -1. No, I can't put any value because none of these are positive. So I don't have a choice of inserting to the left of 1. I hope this is clear. Now consider right side of 1. Can I put 2? That means, can I put 2 over here? No, I cannot put 2 because if I put 2 over here, then this is not a valid BST because all the elements to the left of this 2, see all the elements to the left of this 2 have to be less than 2. But over here 2 is equal to 2, right? See, 2 is equal to 2. So this will not be a BST anymore. That is why there is no option for me to put anything on the right side of 1 also. When I can't insert to the left or right, I have found a dead end. So basically from this example, we have to understand that, what should we understand? From this example, we should understand that for any leaf node with value x, if x plus 1 is present or x minus 1 is present, sorry, x plus 1 and x minus 1, x plus 1 and x minus 1 are present, then it is a dead end. If x plus 1 and x minus 1 are present in the BST, then that leaf node is a dead end. Another better way to check this is, I'll show you the code for that, but I hope you have understood this much. So actually, if you look at the GFG code, they have made use of set. They made use of unordered set or something. Okay. And there, I think the complexity becomes n log n. I think set makes it n log n. I think it's implemented using a BST only. So set makes it n log n. But how to do it in O of n time and O of 1 space complexity? So let me try to show you that. So what I have done is I have written this function which is called bool is dead end. Okay. No, I have not written this function. It is already given. I have to see this function bool is dead end. It is already given to us. Okay. I am actually just passing three parameters, root, minimum, maximum. Minimum is 0, maximum is int max. So actually I can just pass, instead of these two variables, I can just pass this itself. So this is also correct. So basically in this function, I am writing only this much. Now what is this find function? Find function takes three parameters, root, min, and maximum. If at all root is null, we will return false because there is no dead end. If there is no root only, there won't be any dead end. So false we are returning. Now, if max minus minimum is less than or equal to 2, that means we have found a dead end. I'll explain this with another example right now. I'll explain it. But if this is false, then we recursively check on the left side and right side. But what changes we make is what parameters we are passing. See, when we go to the left side of a node, maximum value possible is going to be root data. Actually, max value becomes root data. Actually, maximum possible value which is possible in the left side is root data minus 1 according to the BST property. That is what I'm trying to say. And similarly, when we go to the right side, minimum value is root data, minimum value. And maximum value remains max only. Okay. So we are taking OR, we're doing a OR operation over here, logical OR, because either on the left side or right side, if we find, we will return true. But what is this statement? Let me tell you this statement here. So please observe carefully. Let me consider this second example. The second example is, so this is going to be the second example. Okay. So in this example, let us consider all the leaf nodes. Let us start with 2. So for 2, will it ever be a dead end? See, over here I can insert 3 and over here I can insert 1. I can insert 3 or 1. I can insert 4 also, I can insert 5 also, 6 also, anything. So this is never going to be a dead end. So this is never going to be a dead end. Okay. Let us consider 13 now. For 13, what all I can insert? I can insert any value, any large value over here. 13, I can insert anything, right? 15, I can put. So this is also never going to be a dead end. But what about 9? See, let us concentrate on this node 9. When we are at this node, let me tell you one thing. See, when we are at this node, what is minimum value? According to the program that we have written, according to this program, when we are at 9, see, when we are at this node 9, what is minimum and maximum? So initially minimum is 0, maximum is int max. But when we go to the right side of 8, when we go to right side of 8, minimum and maximum will change. No, only minimum changes. Now minimum is 8, but maximum is still int max only. Okay, now we have gone to the right side, right subtree of 8. Now we are on 10. Now we have come on 10. Now when we go to the left subtree of 10, when we go to left subtree of 10, over here, minimum will be 8, but maximum changes to 10. As we can see from this code, when we recursively check on the left side, see, this is recursively checking on the left side. Maximum, instead of maximum over here, we are passing root data as argument. And when we are checking on the right side, when we are checking on the right subtree, we are passing root data as the minimum, right? So I hope you understand now. So when we are at node 9, this will be the condition. Minimum is 8, maximum is 10. See, for 9, there is x plus 1 also and x minus 1 also, where x is equal to 9. So x plus 1 also is there in the BST, x minus 1 also is there. So over here, I can't insert 8. I can't insert 10 to the right. So this is not possible. This also is not possible. Hence, 9 is a dead end. So that is why this function is, this piece of code is the simplest I found. And I thought this only will be the correct answer. So I will put the link of all the answers in the description. You can check out there also. Okay. So I think this was easy only to understand. Let us move ahead. So now let us see. So there is a problem called given n appointments, find out all the conflicting appointments. Now, what do you mean by conflicting appointments? So conflicting appointment means, so what do you mean by a conflicting appointment? Over here, let us consider an appointment. Starting time is 1, ending time is 4. And another appointment, starting time is 2, ending time is 6. So this is a conflicting appointment because the starting time of this comes in between. So starting time of this is less than the ending time of first appointment. Starting time of second appointment is less than ending time of first appointment. So that is why it is a conflict. So what is the brute force? So brute force method, which will take O of n square time, is for each and every appointment, that is, so for each and every appointment, let us say there are n number of appointments, okay? So if we consider for each and every appointment, that is this for appointment number 1, I will consider all other appointments and find out the number of conflicts, number of conflicting appointments I'll find out, and I will cumulatively sum this. So I'll keep a sum variable and I will cumulatively sum all this. So this will easily take us O of n squared time. So how to reduce, because this is obviously not feasible, how to reduce it? So to reduce it, there is something called as invert interval tree. So you guys need to know what is interval tree. Actually, I myself have not studied this because this is a hard topic, and my seniors and friends told that this interval tree is made of red black tree and all those concepts. Red black and AVL. I am not a CS student. I belong to electrical electronics. So my friends are like, after you do all the other concepts like graph, dynamic programming, then you go to these which are less important. So I myself have not done all this, but you can do it if you wish to now itself. I'll put the link in the description, and you can see this GFG article is very well written, and you can read it completely and try to implement it. But if you have not done it, it's fine. Maybe after doing all the other important concepts, we will come back to this. Okay, if time permits, we will do this. And don't worry, it is not such a important, actually a hard problem only. You won't get it. Actually, you won't get it if you don't see the article. So please do see the article and learn from it. Okay. So finally, we have successfully finished binary search tree. This problem is actually red, black, and AVL tree. It's interval tree. Self-balancing binary tree it is called, but it derives its concepts from here. So apart from that, everything else is done. We will be starting greedy and we will do backtracking very soon. Okay. So thank you for watching till here. Please hit the like button if you like the video. Okay. And I'll see you in the next videos. Till then, take care, stay safe, keep learning, keep growing, and keep coding. So bye. Good night.